So here we have a problem and asks us which of the four following equations properly describes a simple harmonic oscillator. And here I have an image of two atoms, two colorful atoms, and they're held together by a spring. And this is the most generic example of a simple harmonic oscillator because we have two objects held together by an oscillating body, the spring, and so they follow that sinusoidal pattern. So at their most stretched out point, these two have the most stretched out spring, and then in their most closed in point, these two have the most compressed. In other words, to graph this, we would get a sinusoidal graph. So we get something like this to describe how the spring is oscillating. And simple harmonic motion is a subset of the simple harmonic oscillation. Okay, it's an example of simple harmonic. So that's most likely where you heard it. Now, how do we describe a simple harmonic oscillator? So that's too vague of a question. So let's instead go one by one in this problem and see which one best describes a simple harmonic oscillator. So for our first option, we have d squared x over dt squared is equal to negative L over G. Now in this question, or this option, we have a L over G term times some positional spatial variable x. Okay, this tells us that it is sort of similar to that of the pendulum. Okay, an equation for a pendulum would rely on similar, if not the exact equation. And for a pendulum, it works as described here. It oscillates back and forth between two states, right? And it goes to its highest point, and then goes to its lowest point, of course. And of course, its string stays the same length, which is why L is constant and G is constant. And our one spatial variable x describes how far along it is along that motion. Now, to further extrapolate how this function works, we can see that x is the displacement of this pendulum, assuming that it is a pendulum. And of course, L over G describes the length of the pendulum and the acceleration due to gravity. The small angle approximation of a pendulum usually actually looks like this: d squared theta over dt squared is equal to negative g over L theta. Now if we approximate, this is approximately equal to L theta, then we get what we had before. d squared x over dt squared is equal to negative, we get negative not L over G. Thus, this first equation is not one of our options. Let's move to our next equation. We have that the change in x over the change in t squared is equal to omega squared. Now for this, usually, of course, this entire problem is based on your memory and understanding of other simpler harmonic equations. Usually you have this negative sign here. Okay, whenever you have the standard simple harmonic equation, it's usually negative omega squared times x because it borrows from the function cosine. Okay, you'd have the second derivative of cosine as negative cosine. Thus, our second equation is not the correct answer. For option C, we have that d squared theta over dt squared is equal to negative mgd over I times theta. So far, so good. We have the negative sign, some which can be a function or constant, and we have that spatial variable theta. So now let's test this omega term, or this supposed omega. This supposed omega term describes mgd over I, and recognize that I is the moment of an mgd is similar to R, which is the. So really what we have here is a description of a torque and angular motion principles configuration. So we have a relationship between torque and moment of inertia. This would actually give us, because we know that tau is equal to I alpha, what we have here is actually alpha. We have tau over I. So we have the acceleration or angular acceleration times the angular displacement theta, which could be a viable option. Now, let's keep that in mind. Now let's move to D. D describes d squared x over dt squared is equal to negative k over x, k over m. And what you should recognize here is that k over m value is very similar to our spring value. Okay, so far so good. We have the negative and we have a spatial variable x. Either whether k over m is the correct equation to have here. If we're borrowing from the spring equation, f is equal to negative kx, then we know that this would equal to ma. Thus, we get a is equal to negative k over x times, k over m times x, which is actually what we get, because simple harmonic motion requires that we describe acceleration, which in this case is a, which is the same as second derivative of x over dt squared. And thus we get that exact equation. So here we have two viable. Now the thing is, our problem tells us to choose the one that best describes, okay? It should describe a simple harmonic oscillator. And we know, again, that a simple harmonic motion system is an example of a simple harmonic oscillator. Thus, in terms of options C and D, the best option would be D, because C would require us to know how the system is set up. Though it might be true that torque over moment of inertia is the simple harmonic oscillator equation, we don't have the specific system. Thus, D is universally correct because we were able to perfectly get the equation. Hopefully that helps.